So these are simply stable distributions which we use all the time because they arise now.
So how do you see the Gaussian again when alpha equals 2?
Yes, when you have alpha equals 2, here you will get the usual characteristic of a Gaussian, right?
There's a sign P.
There's some additional thing here, exponential, which will cancel with I that you have in front. So you will have some constant which will somehow specify the variance, and this guy will specify your mean. Right? So it will not be like normal 0, 1, but it will be normal something, right?
I see.
It will be normal. Right? That's the only option for alpha equals 2. Okay. And now, why do these distributions rise all the time? Well, because in some sense, many variables are attracted to them, and they're the only things you can be attracted to in a certain sense. Okay. So more explicitly, we will say that x, a random variable x, is in the domain of attraction to an alpha stable variable y, if you can find some suitable sequences of entering constants an and normalizing sequence bn, always positive, such that this guy right here, which is defined as this thing, converges weakly to y, so in distribution to y. Okay, so since y is alpha stable and many properties, it has a density, it's homogeneous, everything. Essentially, you can understand this as the convergence of the distribution function of the thing on the left converging to that of the right point. Okay. And as I said before, it turns out that if you can find constants such that this thing converges in distribution to something, that something must necessarily be sustainable. Okay? So something non-trivial. We converge to 0. Interesting. Okay? So this is the reason why these distributions are so widely studied, right? I mean, we know that, for example, if your variable x has element, then the implicit ELT implies that under a suitable sequence an and bn, for example, an n times the mean of x1 and bn square root of n, you will converge to a normal distribution, right? And essentially, you're just extending this result to all the variables that don't have second moments, right? And somehow this already suggests that alpha stable distributions will have heavy tails, and so not find a second moment. And indeed, this will be the case, right? In fact, if you are to converge to a stable distribution, it is sufficient and necessary that your tails behave like this, so already kind of stable. So just point out x here I'm taking to infinity. So this guy here is referring to the negative tail, and it should have a behavior that's essentially x to the minus alpha, some slowly varying function, and some coefficient in front that we'll call q. And the right tail should also look like this, but with a possibly different constant p. Okay, but note that the power must be the same on both sides, and so will the slowly varying function. Of course, if you have different powers, only the smaller power will dominate, and you would essentially have the same relationship, but just that q or p will be 0. Okay, so the only condition is that the sum of them is positive, so at least one of them is strictly positive. Okay, in this case, you can find, in fact, the explicit constants a and bn that will give you the convergence. And in particular, if you start with an already stable distribution, this guy will not depend on n. I mean, you can find constants a and bn as suggested by the definition of stable distributions, such that this thing that has a law that does not depend on n, obviously converges in law, so obviously it satisfies this. And in particular, for stable distributions, you don't have a slowly varying function. Okay. So in some sense, even here, the slowly varying function is not doing much. Even if you have a slowly varying function there, you can still converge, you can still compute everything, you can conversion distribution, right? So some of the flexibility in these models, or in these somehow strong result, is that even for a given alpha, you can have different combinations of q and p, but that's still parametric, right? That's just like almost two-dimensional flexibility, but you can have almost any slowly varying function. Well, in fact, you can have any slowly varying function there, right? Flowing to infinity, to 0, fluctuating, anything you like, right? And since this is a relatively wide class, then this covers most distributions that you can think of. Create specific or real world distributions. I'm not sure. Okay, so just a remark. In the case alpha equals 2, which is not covered by this thing, so that's the normal domain of attraction. The random variable will be in this normal domain of attraction if and only if this truncated second moment is a slowly varying function. For example, when you have a finite second moment, which is the classical CLT, this function converges to a constant, namely the variance. So, of course, it is slowly varying. Any converting function to a non-positive finite value, slowly varying. And you can, thanks to the regular variation and all these techniques that I showed you before, even though you usually require many conditions to satisfy, with the regular variation, one condition implies somehow all the others, and you can easily characterize all these convergences. Okay. So let me just describe a little bit how you build this constant P and Bn. So if, as I said, if y is of a stable and x is in the domain of attraction of this stable process, then the tails are regularly varying within alpha. Both tails. Maybe one has a constant 0, which doesn't go with that. And you can pick Bn to be function g, evaluated as an integer n, where g is a regularly varying function. Okay. So the main part of the function, so that's the our block here, is 1 over alpha, the same alpha in the regularly varying index, and some slowly varying function f. Okay. How do you work out this slowly varying function f? Well, what it has to satisfy is this relationship here, right? It's asymptotic equivalence, right? So if what you have is the asymptotic expansion, let's say, of the tails of the random variable x, you somehow need to almost invert this tail, right? Not exactly invert because you don't want x on the right side, you want 1 over x. But it's almost inverting it. That's how you need to select the little g. So often, if you know enough information about your random variable x, you can work out what this little g is. Okay. And what about the centering parameter? Well, it turns out that if alpha is strictly less than 1, then you can pick an to be 0. It doesn't matter. It will be eaten up by the scaling normalizing parameter Bn. And if alpha is greater than 1, then your random variable x will have a finite mean, and you can pick an equal to n times expectation of x1, just like in the short CLT. So more or less things as you would expect. It's still reasonable. So now some definition of why I'm raising this cautionary tale when I warn you apart. So if the slowly varying function here has a positive finite limit, this limit exists in 0 infinity, which somehow means that the expansion of this guy also has a slowly varying component. Right, so essentially, if you can describe this case, you can find them as x2 should be minus alpha, then L hash x. So this guy has some limit in 0 infinity. Then the curly L over here will also have positive finite limit. And if this guy is in some sense properly slowly varying around the function, so maybe it's log 1 over log, then you need to work out what the curly L is, and that curly L will also not have a positive finite limit. Okay? It's not exactly its inverse, it's not exactly anything like that. It's usually called the Brugian conjugate. And sometimes it's easy to work out, sometimes it's not. Usually if this guy is some power of log, this is another power of log. There's some nice relationship, which you can usually work on. Okay. And in this case, for a positive finite limit, we will say that x is the domain of normal attraction, not the normal domain of attraction. Okay. So the attraction is normal, not the limit. This is a I don't know if this is a came up with this, but just something to pay attention to. Okay. If this slowly varying function is somehow properly relevant, then we will say that x is in the domain of non-normal attraction. Again, the attraction is the one that's not normal, not the domain of the limit.
So what was the relationship between X and Y? Here.
X is some relatively generic distribution. So somehow aparametric, non-parametric, and Y is alpha stable. So Y has the characteristic function that I gave a few slides ago, and X has something. And the only thing we know about X is this thing, right? This condition on its tails. But let's say for finite X, it can have anything. It can have jumps, no, it can be singular, continuous, whatever. And the Y has a density, it's infinity, it's super nice. Okay, and all you know about X is tail behavior, so just asymptotic equivalence. Okay, and maybe even on one side you have a Q positive, and on the other side you have a P equals 0, which means you could have discrete all the way through. Right? Right? So in some sense, you're asking for very little out of X, just some tails as well. Okay. Does that answer your question?
Yes, thank you.
So there's this classical result by Peter Paul, and there's many more of this flavor that help you control the speed at which you're getting these weak convergences. So first, before I go into the details of this thing, why would you want this? No? So in practice, you have the real X, and what you will do is somehow estimate it with the limit. This is somehow reminiscent of what Umut said or used before. You want to estimate, say, this tail. You don't know exactly, you just know some asymptotic figure about it. You want to somehow estimate it with the limit plus some error, right? Okay. So a good way of doing it is, well, this guy, of course, you can just write it as the difference of the probabilities. X minus probability. This such a big camera. It's hard to tell.
Camera is.
Of the no.
It's probably just recording the screen, isn't it?
Do you think so? Yes.
It's difficult to flip, yeah.
Yes. So, I would want something like this, but now for the nth approximation. And what is this n? This xn will be xn divided by minus n divided by b. Right. So this is the guy that converges distribution to 1. Right. And in practice, what I want is somehow to study this guy. And somehow, in this case, since y is very well behaved, we have ways of computing this thing numerically, power expansions, integral forms, and everything. I can sort of compute the tails of this guy in terms of its tails plus some error, right? So how good is this approximation? Well, obviously it depends on this error, which the analogous would be this generalization error plus the limit. No? So how does this compare to the other one, right? For example, if I want to estimate very large this probability for very large value of x, and I want to use the limit, which I can compute, well, I better have a very small value here as well, right? Because on a rare event, this is a tiny thing. So if the correction is much larger, it doesn't really help. Make sense? And since this guy is, well, proportional to this thing, right here, well, essentially, if this error, how large can I take the x? Well, I can take x to get reasonable values, more or less up to error and power minus 1 over all, right? Different constant. Yes. So if this error is, let's say, polynomial in n, that means I can take x all the way to polynomial n and still get reasonable estimates for this tail probability. Whereas if this error is slow, let's say logarithm, I can only go so far here, right? So even though you're converging to something that's heavy tail, maybe it will take you an exponential amount of time to converge to become heavy tail. You don't know. Does that make sense? right? So this could be polynomially small, not exponentially small. But the correction error is so big that this could be thin, and it takes you an exponential long time to become heavy. Much like in SGD, if you have thin transitions, light tail transitions, it can take you an exponential long time to get out of any local minimum. So these could actually ruin your game. This thing is important, right? This error. Of course, if we're moving the x here, it's hard to control the error, so you usually take something like supremum of these differences, which is known as Kolmogorov of distance, right? Which is the worst case scenario. You never know where it's actually happening. Okay. So does this all make sense in some sense? Okay. Yeah. So we've had more or less motivated by something similar. Was developed this in the classical setting of CLT, normal domain of attraction. You have this celebrated result Berry-Yassine bound that says that if you have a finite third moment, although it has been weakened later, you can really control the supremum difference between these two distribution functions. Yes?
Is C naught 1?
Is 0, 1, sorry.
C naught equal to 1. Is it 1?
C naught?
Yeah.
I mean, it doesn't matter.
L of x tends to 1.
Yes, you can absolve the constant. Yes, you're right. Okay, fine. Converge to C naught. You're absolutely right. Yes, you're right. I'll get you this first.
Could I comment? You said one can control. When you have capital O, I don't say about real control. I would say if there was a bound, you would control with known constant, but a capital O of something doesn't give you control.
Capital O of something gives
Doesn't give you control, no.
Kind of control.
Kind of control.
Yes, it gives
Capital
you-
like maybe million, maybe billion, billion times something. Okay.
Yes. Maybe it's a very large constant in front of you.
Yeah, maybe not constant.
Maybe not constant.
Yeah, maybe varying, you know. Well,
Okay. So the celebrated Berry-Yassine theorem first gave you a bound explicitly in terms of some 2 plus epsilon moment. Okay, for this error term in the domain of attraction of normal distributions, and there's many versions of this theorem with changing parameters q, maybe taking a different metric, not necessarily Kolmogorov, different metrics,
but no with bounds.
but no good bounds.
No with bounds.
No real bounds, you
No
mean?
bounds.
Yes, okay. In the very general case of random walks, you're right. In fact, even here, there's some funny restrictions on where Q should be, right? For some reason, they require to be larger than alpha, even though you would expect to get something, even if you pick a relatively small Q, as long as, Anyway, this is more or less classical result by each Hall. And essentially, this is the Berry-Yassine theorem, but for heavy tails. When alpha is larger than 1, then you have...
Excuse me, please. Why do we assume that Q is greater than alpha? If it was x to the minus alpha plus big O, it would be.
Yes, probably it's
It would make sense. No, it's not. For some reason, it's not. So, yes, it is also very possible. I've not looked exactly at the proof. I know that prior to this result, someone had considered the case where you have also minus alpha here. Why?
I would
the
ex-
question
I
is like you multiply x to the power minus alpha
But by
times
extra- by
x to the power
extra,
minus
yeah.
q.
Well, I think the reason is somewhere in their methodology, this does not give you something.
I would expect Q just positive.
But you see, one
Yeah, you're right.
Q-
It's just like
yes,
the 1
I
minus
agree
q.
with you.
Yeah, okay.
I agree that there must be some theorem out there that's like that. But you see this bound?
Because they're not optimal.
Just bad bound.
Well, okay, fine. It's just a bad bound, not non-converging bound. Sure. It's either constant or exploding. Not very good. But in any case, so the original result, or the first result, required Q equals not more. It's not very good, and the convergence is not very good. Guarantees are not very good. But if you're very close to being already stable, so the correction term is also polynomially small, so on top of this 9.5, then you can control the Kolmogorov distance between the distribution of this guy and y. So my x n y, and it decreases polynomial. Right. So that means this error term polynomial in n, the power function of n, and therefore I can go as large as some other power of n here for the tails, right? For my estimates.
So what does it mean, second order collision?
This is the second order condition. So this is the first order and second order. So somehow you go to the next polynomial term, Okay. So in these Taylor somehow suggested of these Taylor expansions. First order is a linear term, quadratic, and so on. But somehow this next correction order. But it's just in the form of some big O. It's not exactly it's logically proportional. Okay. So there's now more extensions to this slightly improved bounds, but not so much more, and it doesn't much matter for what I want to say. Okay. The main takeaway from this is if your slowly varying function is not really slowly varying because it's converging to a constant, so that you could actually ignore it here, you would still get your asymptotic equivalence there. You will still get weak convergence from this guy to one. Then you can have some decent, just decent control in the Kolmogorov, in this error that I want to control. Yes. Okay. And you can change the metric if you want to use a different metric because you're not certainly interested in that. Maybe some more asymptotic or something else. You can change it. And there's some results in that direction. All right. So good thus far? Yes. So this is what I just said. Okay. Now I will give you the cautionary tale in terms of something called the lifetime distance. But some people, namely Bergers and Greengard, have proven it for the crocodile distance, which is what metrises weak convergence. So maybe it's like maybe the metric. Okay. But the proof is more involved, so I'll go to the easier proof, Q-Washstein distance, which is still of interest because I think it's been gaining popularity in recent times because it's the minimal transport and all this. Let me first introduce it. So I will denote by WQ, X and Y, the Q-Washstein distance or L-Q-Washstein distance between two random variables X and Y. Okay. So even though it's written in terms of X and Y, it's really the distance between their laws. Okay. And it's defined as the minimal possible distance in LQ. I need to sometimes take root 1 over Q if Q is larger than 1. Otherwise, I will take it. It's not a norm, it's a metric. This is a distance. Okay. The minimal expected Q distance, where I consider all possible couplings of random variables psi and zeta that have the same marginals X and Y. Okay. Yes.
Does there exist a dual simple metric for this one? It's a it's called complex metric, which
It's a
depends
complex
on your
metric.
distribution. Does there exist a dual simple metric for this?
Does there exist more simple metric?
Dual, you know,
Dual.
duality between simple and
Yes,
complex
yes,
metrics. Does there
yes.
exist
So
a
the answer
dual?
is sometimes. So for Q larger or equal to
Q
1,
equal 1 to
there's
1.
there's a dual in terms of expected.
Yeah, it's a simple one. It depends only on marginal
Well,
distributions.
simple one. So this is more probabilistic. The other one is more analytical, I would say.
We will talk later. Okay.
Yeah, we can discuss that. But Q is more than 1. There's just like one-way inequalities. So you can control one with the other. You put some equation on that. Okay. I like this one because it's variables on some space that are very close to each other on average. Right? There's a way of measuring things. And as I said, you can use crocodile distance, which is what metrises the metric. The progress is here. And as I was saying, this infimum is taking over all couplings, psi and zeta, that have the same marginal laws X and Y. Okay, so psi has a distribution of X and zeta has. Okay, good. Then there's very simple lemmas, and this is what somehow gets complicated with metrics. So the first thing is the Q-Washstein distance between psi and A psi, where A is just some constant to 0 infinity, is bounded below. So these lower bounds are hard to get usually for different metrics. Bounded below by 1 minus h to the q times the q moment of psi. Okay. Oh, sorry. Another thing to mention I'm doing this in the real valid case, but you can do it in RD. I mean, nothing really changes. I just have to explain it here. But everything holds. Oh, let's see. Okay. So this is not so hard to believe. You can almost look at this, put xi, notice that you can take it away and take it out and put, right? Now, of course, that's just a coupling. And what about any possible coupling? Well, you use some of these duality representations indeed. Okay. But it turns out it's a relatively simple thing, and you would expect.
I'm sorry, what happens with A equal to 1?
You get nothing, right?
Like to 1 left hand side is 0.
Distance,
Left hand
one
side,
random variable and itself is 0.
right, but the right hand side is not 0.
Yes, it is.
Zero as well.
One to the q is 1, and then 1 is
Oh, this is, I forgot the parentheses are over there. Sorry, I did not see where the parentheses are. So you, it's,
it works. Yeah, it's
okay.
Surprisingly.
Yeah, you get 0 or greater than 0. All right. So moreover, you have some kind of, it's not exactly triangle inequality, but it's somehow attraction property, which is that if you take pairs of independent variables and you compare xi1 plus xi2 versus zeta1 plus zeta2, you have this inequality, right? It's less than 2 of these distances, right? Okay. Not too hard to see or prove, more or less natural to believe, yes. So triangle inequality. And again, this works because I'm dealing with, I mean, I solve this sort of inequality like this, I take out everything, and then I just say, oh, infinite everywhere, still. The proofs are follow relatively easily, and if you take all the metrics, it's not as easy. But some similar results. Okay, so this is my first ingredient, or my only ingredient. Fact.
As you see.
This.
Outside.
So now I will assume that you have a random variable x that is centered. That means it has 0 in, so I can use this little an. Okay, and it lies in the domain of attraction of 1. And in fact, I will assume that it's not important for what I will do here, but I will just assume so that you do not have to worry about having a little 1 here. I will assume that you have a proper slowly varying function. Okay. So my constants Bn are this function evaluated at the integer n. This thing that I have right there where an is 0 is the guy that's converging to y. Okay. And you have this bound. Okay. What does this bound say? Okay. First, a of x will be curly L, so the slowly varying function, evaluated at 2x over the curly L at just x. Okay. So somehow it just went from time x and twice the time. Okay. So obviously, if curly L converges to a constant, well, if curly L is slowly varying, this has limit 1. Okay, it's a nice boundary function. It converges to 1. If L was constant, then I would just have 1 here, and I would have 1 minus 1, and the lower bound is 0. Now, if I have a proper slowly varying function, then this thing here, which is just a constant, not blowing up. And this other thing here also converges to a constant, in fact, 1 power cubed 1. I will have the sum of 2 distances. So the distance from x at, let's say, time n, for the approximation at the level n, and approximation at level 2n, the sum of these 2 distances is lower bounded by some q moment that does not depend on little n, and the only dependence in n is in this thing. Okay, which we know goes to 0. What we have, because we have slow variation, so it makes sense. I mean, it's not contradicting anything. Okay. So what I will use about this is that I will prove that very often this thing is slow. Very, very slow. Okay.
So there are 3 random variables here.
Yeah.
xn, x2n, and y.
So the approximation level of time n, twice that time, and the limit. Okay. Yes. And I could have taken not 2n, but 3n, 4n, another constant. I would just have to modify a here slightly, and the constant will come in. You can do it. Fair enough. Yes. So essentially, I mean, in fact, we can imply this. The maximum between these 2 distances is lower bounded by some. And I will prove that that something is slowly going to 0. It is going to zero, but very slow. Okay. All right. So the plan is set up. Yes. All good. So first, I will give you a tool to show that it's
Why is the maximum lower bounded by the set?
yes. So twice the maximum is larger than this.
Okay.
So I just divide it. Okay. So I mean, either at time n or at time 2n, you're not very close, and you never know if you're at one of them, and maybe neither of them is close. Okay. So it's not like, oh, along some funny sequence of times n, you're away. No, it's like half the times you're away. You're very far away. Not polynomially close. Okay. So just this is to show you that it's a really elementary. Okay. So from the definition of stable distributions, y has the same distribution as 2 minus 1 over alpha y plus 2 minus 1 over alpha y prime, where y prime is an independent variable. Okay. So then I simply write some things and apply this lemma that I give you. Okay. So I have this an function, which is curly ln at 2n over curly ln times the approximation of time 2n versus 1. Okay. So this I will write as I will rewrite each side of this Bashtan inside. So first, this guy is simply s2n minus sn and then plus sn. Yes. Nothing surprising. And on the other hand, I have the y and the y prime. Why can I do this? Because I'm just comparing really the laws. I mean, I'm somehow abusing notation a little bit, but I'm just comparing the laws of things that, okay, so I can replace it with anything that has a thing. Yeah, just for visual effects. Okay. Then I'll use the second part of that lemma, and which says that this distance is bounded by the distance between this guy and this one, and this one and this one. Okay. Since they're both have the same law, this nice random walk setting, I will just have a factor. Okay. And inside I will have Sn over this denominator and y over this other factor. Okay. Yes. Now, because Bashtan distance is nicely defined, I can take out the factor 2 to 1 over alpha that I have here and here. Okay. Now I get it here, it has power q because I have some q moments, right? And I have here the Bashtan distance between x at time n and y. So I have some relationship between x at time 2n and y with some constant versus x at time n and y. So this is the one of the two steps. Okay. Now I will note that this thing here is equal to that one because again I can just take out this constant factor outside the power q. I can the expectation and then it doesn't really care about the coupling, so it does nothing to it. Yes. So nice and well. And then I finally get my bound. Okay, so the left-hand side of my inequality is greater or equal to this thing. Yes. So the second bit of the second term beats the second term here because of this inequality that I have also. Right? Remember, this is an. This is the an that I have here. Okay. And the first one, I simply what did I do? Sorry, no. This one is the one that beats this term, and for the other one, I simply put the an inside the both. Okay. And then I use my first part of the lemma, which is like some kind of a triangle inequality, right? So now I have the same factor here and here, but I have some y and a and y. So triangle inequality means I beat y versus itself with a inflating constant. Okay. And then I will just get the moment, q moment of y, which does not depend on n, and this is the only factor outside. Okay. So that's the result. Right? Very basic. There's analogous to, I mean, it's more elaborate to prove, but you can do this for Prokhorov distance, right? And many other distances. Sure.
You're using Q. Q is smaller than 1? Or?
Yes, yes. So I didn't emphasize that enough, but here you see that Q is between 0 and 1. You can do Q larger than 1, but I would need to consider the possibility of having square root 1 over Q in the definition of Bashtan distance. So just to ease my life, I will consider this easier case, but you can treat all the cases. Just it doesn't much change. It's all very, very elementary. Are you using any deep? Okay. Is there any other questions? So now it's all about this function an. How fast is it going to one? So this is the one of the main lemmas that describes how fast this thing is going. So I'll consider slowly varying function L, that will be C1. Remember, this is not really a restriction because if you have a slowly varying function, it's asymptotically equivalent to a C infinity slowly varying function. The actual restriction is that I will assume that the derivative, which must look like this, is eventually positive. Okay, sorry, it's eventually has a single sign, so it's not changing signs. Right, so that means that curly L or something related to curly L is eventually monotone. Reasonable. So we can do an example. Let's check what this looks like.
What is the density of function?
Sorry.
What is the density of function?
Derivative.
Slowly varying function with density,
Derivative.
derivative.
Yes, derivative. Yeah, maybe I should have written something like that, right? I don't know for reason. Let's do some examples here, right? So let's imagine I have a f of x equals x, then derivative, which is going to be 1 over x. That means L tilde is constant. Okay, so indeed it is eventually positive. I mean, if I take the modulus, it's eventually positive. It's always positive. If I take 1 over log, then I will get 1 x log squared. Right, and the modulus will be modulus of 1 over log squared. And this is eventually positive. It's not changing signs. That's what I mean. All I care about is this guy without the modulus. If it's negative, it stays negative after a while. And if it's positive, it stays positive after a while. Right? Eventually, it's not fluctuating. Okay? This is important for slow variation, like I said before. And you can do log, many other examples exist. You will need to find something very fluctuating to not have this kind of property. Okay? Yes? We're all happy with this? So this actually covers many slowly varying functions that you can think of quickly. You need to work hard to construct something that's not within the scope of the lemma.
Sorry. L of x, the only thing, if it has a density, then the density is equal. If you look at the representation theorem, then L, the only thing you know about L tilde is that it goes to 0. You don't know
The
anything else.
representation theorem has e to the minus integral.
Yeah, I just wrote it down here. And so L tilde, I'm gonna like we should be able to discuss this or not.
Sure.
Okay.
Yeah.
So the representation theorem says e to the power integral 1 to x, and then h of u over u. So because I always thought that there needs to be some monotonicity assumption that the derivative of a regularly function is regularly varying with one index lower under some extra assumptions. So I was surprised.
It's not a result. I'm putting a condition on L.
You assume that
Not
L,
any slowly varying.
so you assume that L tilde is slowly
Yes,
varying.
I'm
Okay.
assuming
Yeah.
that this guy is differentiable and that its derivative, when I put the modulus on this L tilde, is slowly varying. This
Okay.
did not happen.
Then we're all good. Yeah. But you assume that L tilde is slowly varying. It's not part of the lemma.
It's part of the assumption. It's
Okay,
the
good.
conclusion
Okay.
in the second sentence.
Yeah, sorry, continue. And then I understand it.
Okay. So in fact, you can start from the other way around, right? If I start with a slowly varying function that satisfies this, I can construct the L.
Yeah.
And it's always slowly varying. So if I start here, that one will also be
Yes.
always be slowly varying. Right? This is one of the theorems that I gave out. Okay? So let's maybe an easier way. The recipe to build this button. So now I will define this capital L lambda, which is precisely the thing that will go to 0. Yes. If I pick lambda equals 0, I get exactly the an. Well, 1 minus an to the power 3, right? Then you just write back. The definition here, this thing right here. Yes, this is essentially the lambda, L lambda, or lambda equals 0. If you see, it has a power q, so it means that this curly L is not the same curly L as there. It's curly L to the power q. Okay, but still slowly varying. Okay, so nothing changed. Okay, all good. Okay, so this thing I put a modulus, so I make it positive now, okay, or non-negative, will be slowly varying, and it's asymptotically equivalent to this. Okay, so I can even work out how slow it is. Right, so again, let's just work it out. Lambda just gives me a multiplicative factor, so I will ignore it. I just need to compute modulus of L tilde. Good guy. Over L. Right? So in the first case, where I had log, I got constant 1, so I had 1 over log. Okay. If L is 30. And if I have 1 over log, then what do I get? I get 1 over log squared, modulus, and then over 1 over log, I also get 1 over. Okay. So indeed it is going to 0. And in fact, I can work out how fast. And the log lambda is just a factor. Okay.
Is that like a result? Like, is there like results like that in the? You have the big and go circle book, chapter 3. There are these second order results. It kind of smells like that, right?
It smells like that, but for some reason it's not there. Yes, I mean, it is surprising. So I said this yesterday, maybe I should have emphasized it more. This quotient is going to 1, or just 1. So any slowly varying function, that's the definition of it. And some people, and the convergence is uniform in lambda for compact sets. Okay. And some people have studied how fast this happens under certain contexts. But I guess they were not motivated enough to look at just how fast or how slow it can be. Why? Yes.
My recollection is that uniform convergence on compact sets is automatic, right?
Yes. Yes, this happens for uncompact sets, yes. Lambda compact sets. So for branch.
If all X, then on compact sets.
Yes. Yes.
Sorry, if all lambda, then.
If for lambda, then it holds, yes, uniformly on compact sets of lambda. Yes. Yes. But the question is, I now want something quantitative. So how fast? Like really how fast? Okay. And then this is how fast. Okay. Under most for most curly L's. There's some assumption. It's not a theorem. That's not for every slowly varying function, but for most that you can come up with, it will happen. L doesn't even need to go infinity. Just take it. Okay. And the proof is in fact dominated convergence theorem or uniform convergence theorem. Okay. So this is what I was saying. That if you pick lambda equals 2, means that this thing will be slowly varying and you can work with how slow. Okay. We'll get. Let me just give you some examples here. So we worked with a sub-example of this one with p equals 1 and 2 equals 1. You can do also log p or log x for some p equals 0. And you can add them, impose them within the operations, and most of these things will still fall in the scope of the thing. Okay. But who knows most of the slowly varying functions that somehow appear in the world. And the proof is it's not hard. Okay. So first I will show some limits, and then I will use it to prove the slow convergence today. Okay. So you write L of CT minus L of lambda CT over the curly. Okay. So I write this L as the integral of its density or derivative. Okay. And then I use the fact that this dx over x is now scaling variant. I think it does. Okay. So that all I need to do is put the CT inside the curly. Okay. Now the integration set is from lambda to 1, and then I put the 1 over lambda over L tilde, sorry, inside the. Okay. It's not being integrated. I just put it. Okay. Now the uniform convergence on compact sets, lambda compact sets, does this guy converging to 1 uniformly, or if you want to dominate it, so that the limit of this thing is just this integral dx over x, which is minus log lambda. Okay. So nothing weird yet. And then, so I will now use this limit to show this other thing. So first, slow variation. I take the capital L lambda CT over a lambda of T. Yes. I multiply and divide by L tilde to the minus 1. And then I note that this thing and this thing are the things that I computed before. The limit of both of these is minus log lambda. So it cancels out. And I just get, so this thing will have limit 1. And then this thing here by the slow variation of the initial function will also go to 1. Okay, so this thing goes to 1. So why did I put the modulus? Well, because this capital L could be negative. And the slope variation is for positive functions, so I just need to. Yes? Oh, good. And to show the asymptotic equivalence, I need to do something very similar, where I now compare L tilde with, L lambda with this function right here, and again follows one of these limits. Let it go away. Okay? Nothing. Just happens. Okay. Now, okay, so I have a way of working out this thing, but it's not very clear how flexible this thing. Okay, right? I mean, you have some slowly varying function, then its derivative somehow, or the slowly varying component of its derivative and the quotient of this. So can this be just anything? Well, the answer provided by Burgers and Greener is that not really, under other conditions. So if your slowly varying function little l goes to either 0 or infinity, so again log, or 1 over log, power on 0 power, then this name soup is infinite. Okay, and again have a 2 here, but you could have 3, 4, or any other concept. Right. So morally, what this says is that you cannot go faster to 0 than logarithm, or logarithm of 1 plus epsilon or something. Yes? Do we all see that? So this thing goes to 1, this thing is blowing up, and this thing always beats this one. Well, usually, not really. Always beats it. Okay, so you somehow cannot beat logarithm, ever. Right? No matter how small the curly L is. So let me just, well, maybe I'll emphasize this later. Fine. The proof is also very elementary. You write log of L at powers of 2. So it's telescopic sum, so you can't ever count this out. You get the first term and the last term. Assuming, let's say, L goes to infinity, this guy diverges, so that this thing is not summable. So if you put modulus, it's not summable. Should have had an infinite sum, it's not summable. And since these terms go to 1, I have some asymptotics, like two-sided asymptotics, and it implies that 1 minus what I have inside the log is also not summable. All right? And if these were not true, so this guy would dominate this one for some positive epsilon, then this should be summable. So this is a contradiction, and right? Why? Because, well, log of 2 to the k will give you 1 over k, so I would have a power of k that's larger than 1, that would be summable, right? So that's it. That's the gist of it. The other case follows similarly by considering 1 over earlier. Okay. So now a little faster. Okay. So what's the moral of the story? Is we go back, we look at this lower bound that I gave you, and note that 1, this thing is most likely very slowly varying, and I can work it out. So in particular, I can give you a slowly varying function little l that makes this as slow as you want. So let's say you want slower than log, or 1 over log, 10 times, so 10,000 times. Well, I can produce a slowly varying function that gives you that slow convergence. So I can get arbitrarily bad, just arbitrarily bad, okay? Moreover, if your curly L goes to infinity or 0, you will never beat log, or log of 1 plus epsilon, 1 over log of 1 plus epsilon. So the error here will be slow. You will never beat log, regardless of how slow your curly L is, and you also can get arbitrarily bad. Okay? Arbitrarily bad. So why is this bad, right? Well, it means that in your estimation of the tails, you can only go to logarithm of n. So you really need a very, very, very large amount of samples to get just a bit further away and get some nice estimate on your tails. This really completely ruins your convergence for some strange reason. And this happens even if I take L of x to be, let's say, log x. And why am I putting this function? Well, this function you would need God knows how many iterations to see this move from 1 to 2, right? Your computer probably doesn't have enough lifetime to produce enough simulations to get from 1 to 2. And still, so in practice, you will never see this slowly varying function, right? It's impossible to measure this. And still, if it's somewhere hidden there, it's enough to ruin your convergence. So it'll break everything. Okay? So this is the cautionary tip.
So how important is it to choose Q smaller than what?
To choose, sorry, what?
Like Q is always small, right? So
I
mean,
it's not
if-
important. I chose Q smaller than one, just so I could also make it always smaller than alpha, so you always have a finite number here.
and then like the
But if you choose
Modulus
larger than
story
one,
doesn't
you can
change.
do some things in there. You get slightly different things. You get some cube root outside of the modulus. That doesn't matter, right? I'm slowly varying, so another power, it's still slowly varying. The conclusion for the logarithm will be slightly different. It has some power of it, but still. Yes.
What is special with number two here in proposition?
What
Two-
is special
two,
about
number two,
nothing?
because if you
You can
replace
do
the two
three,
by
four.
C, by C,
You need an instant, well, okay, you can put
C integer part, of course, C, for any C.
Yeah.
And-
Yeah, you see the proofs are nothing, right? I mean,
No, but essentially, if you do it, because if you have C, any C, you include the case C equal to one, then A is
oh, no,
one.
okay.
Yeah, it's okay. Yeah, and
C
if-
equals to one gives you L of X over L of X.
Yeah, and you get the particular, should have the previous result.
Pretty default.
So if C equals one, you have just two times the same. You have, you know.
You get a one
Zero,
right? So you get
zero.
on the right.
But it's still true.
So you need
True, yeah.
non one, or C. Yes, you can do it. You can do it, everything in the proof follows, just put slightly different things. You maybe need to expand this, put it for a rational, some equivalent version of this. You can extend it. It's not particular, even this other lemma, it's written for any lambda. And even the proof of this lemma by Burgers and Gringard, it's not too specific about two. I mean, they took powers of two, but of course I could take powers of C here. Nothing changes. Nothing really changes. But I mean, the model sorry doesn't change. The two is not very important. Yeah.
Well, more like, yeah, I like the result. First of all, I would like to say, I like the result, but the elephant in the room is we will not even be able to estimate alpha properly from beta.
Yes, this is a cautionary tale. Right? I mean,
Yeah, okay, but suppose we would be able to do it, then this will be the next endless, yeah.
well, it's somehow a hard limit on what you can do, and I don't understand. I mean, I can give you proof of why, and it's because this convergence is not very fast. But like, why should this be the
So how old is this result of Burgers and Greengard? I never.
2018 or 2019? I don't remember. It's very recent.
Yeah,
Somehow this eluded anyone's attention. No one was. People usually consider, oh, the process to the limit. And these guys, for some reason, said, oh, first the process, twice the time, and the limit, and some inequality. So the fluctuation of L cannot let you converge very quickly. So it's not a lower bound on the distance at any time n. It's either n or 2n, but you're never sure if you're on the bad side or on the bad time. And half the times are bad, at least. Right. Yeah.
And epsilon is only in the conclusion, yeah?
For every positive epsilon, this limit is in. Fixed epsilon, not moving epsilon. You can move, you can weaken this. You can put log
So
n,
it-
log.
Then I don't understand what means one was epsilon, if epsilon is any number. It's heavier than any power of log, yeah?
Yes.
That's it.
It's also heavier than log, well, 1 over log times log to power 1 plus epsilon. You can always push. The point is that once you evaluate the function that you put here at powers of a geometric series, it should not be sum of. So you can construct many other things. You don't need it to actually explode, you just need it to explode along the geometric sequence you're putting, so you can weaken this a little bit. The model doesn't change much, in my view. There's very little wiggle room to move any further. Okay? And you can get exactly log. Yeah. Right. In fact, in these two cases, you get exactly 1 over log.
Okay,
So
I
it's
understand.
somehow not very improvable. There's very little room to improve. Okay. So
I got it, yeah.
ran, but if you give me a few minutes of your time. Okay, I'll skip this. Umut already gave some results for these perpetuities. I'll also go through this. What I wanted to point out is that there's many cases where you have light-tailed objects converging to a heavy-tailed object. And what such case is the case of Levy process. the ones that I need to introduce very nicely. So you can have a what people call CGMY or temperate stable Levy process, whose Levy measure near zero, near the origin, resembles a stable process, but has even exponential tails. You can have even bounded jumps. You have moments of any order, non-engineering function, or problem height for any parameter. It can all be fine. But as you zoom in, so learning rate goes to zero, you have an SDE discretization in short time. In these regimes, you look more and more like a stable process. You have some weak convergence to a heavy tail object, necessarily, unavoidably. Okay? Even if you start with something very light tail. And turns out that under some mild assumptions, you can also rescale your process to converge to a state for an alpha state process. Maybe symmetric, maybe not, doesn't matter. Okay. And if you want hardware, you can get both upper and lower bounds on this Q-Washington distance as well. And much like in the story of random walks going to the case, here, as time goes to zero, if you're in the domain of normal diffraction, you can get a polynomial below and above, it's different constants. But for most Qs, they will be the same rate. So this is very tight and nice, and in particular, you don't have much room to improve. So the convergence is fast, guaranteedly fast, and you cannot get much better. But again, if you have non-normal convergence, domain of non-normal attraction, then you will have both a slowly varying function that lower bounds your distance, the matching between these two, and a lower bound that's also an upper bound that's also slowly varying. And if you're careful enough with these things, you can make them equal. And again, this thing here has to do with this AN that I defined before. So very often you can never beat low, even if you have low flow, something unseeable, perhaps. So it's just a cautionary tale that these can arise even in very simple settings. So I wouldn't expect it not to arise in more complicated stuff, right? And I think that's the thing.
Thank you.